Welcome back, everybody. This is going to be part 1 of 2 in my lecture series on inverse functions. Let's get started. The idea of an inverse of a function is the question, can functions be undone? What I mean by that is, with a function, I've got some sort of rule that tells me, given this input, I get this output. So is there a way to look at an output and know what input it came from? And the answer is, well, sometimes. So first of all, let me make a little bit more explicit what I mean by an inverse. If f is a function, then the function, it looks like f to the negative 1 power, but this is maybe a little bit of an abuse of notation, is the inverse of f if when I plug f into f inverse, I get back x. Let me explain. F of x, remember, is the output you get from the input x. So the idea here should be that if I plug in an output, I get back the input from whence it came. Similarly, f of inverse at the end of the day, or f inverse of x at the end of the day is an input, and when I plug it into the function, I should get back the expected output. In other words, f and f inverse cancel each other when you compose them together. So, for example, before we actually get into the details, let's suppose f is 4x plus 5. I would like you to verify that its inverse is x minus 5 over 4. The way you would go about doing that is watch what happens, when you take f and plug it in to f inverse. Theoretically, we should just get back x. Well, here, f inverse is input minus 5 all over 4. Up top, my 5 and negative 5 cancel. I'm left with 4x over 4. And now my 4's cancel, and I'm left with x. So sure enough, that's the inverse. But here's the problem. Not all functions have inverses. For example, let's consider the function y equals x squared. What input gives you an output of 4? Well, you're probably thinking to yourself, 2, right? And you would be right that 2 is an input that gives you an output of 4. But so is negative 2. This is a problem. There isn't a one-to-one correspondence here between outputs and inputs. Remember how functions had to assign an output to each input, right? And at most one output to each input. But the other way around isn't necessarily true for it to be a function. We do, however, have a name for those kind of functions. So, when does a function have an inverse? When there is exactly one output for each input is the answer. I have to be able to track back to exactly which input the output came from, but if there are multiple inputs that give that output, I'm sunk. So, a function that has this property is called one-to-one, or injective is a fancy name for it. And we have, similarly to a vertical line test, a horizontal line test to tell when functions are one-to-one. If you can pass a horizontal line over the graph of a function without it touching in more than one place, it's one-to-one. Let's look at some examples. The one on the left here. Notice that I can pass a horizontal line over the whole graph on the left without it touching the graph in more than one place. So this one is one-to-one. On the right, it's not the case though. Notice up here I'm fine, but once I get to here, now the graph is touching that horizontal line in 2 places. And in fact, 3 places here. The problem isn't that this is a function, because it's still a function. Notice it passes my horizontal line test just fine. Or excuse me, my vertical line test just fine. This is still a function, but it's not one-to-one. In this video, we looked at when functions have inverses and what they look like. In the next video, we're going to learn how to actually find them on our own. Catch y'all in the next one.